All right, we left off on here. Is that right? Yes, I know one back, so I'm thinking about this one, okay? Now, how'd you guys enjoy Dr. Schechter earlier today? I'm sure Ted will filter this out. Okay, so this is a diagram of a wellbore from 1935. Dahan, what was going on in 1935 in Turkey? You guys had just rescinded cannibalism? Yeah, okay. Mr. Stone, where were your relatives swinging from the trees in 1935? Alabama? No? So this is an open hole completion. Do we still have open hole completions? Yes, no, maybe? Yeah, we do. Okay. And then we have this thingy pipe, whatever it's called, casing stuff that goes up to the surface. We have a valve, we have a gauge, we have a swedge, and we have a T, we have another gauge. They got this thing called a dead weight tester, and it's like a prehistoric pressure gauge. It allows you, by using a certain diameter of a tube, and you put a weight on it, and it's got a sort of a frictionless bearing, and you spin it, and that gives you an indication of what the pressure is. It's accurate. It's a prover for pressure. So, and yes, we still use this as well. So basically, even though this came out, 74 years ago and probably was in play for 10 years before that, we're still completing wells this way. We're still using the same kinds of measurement devices, same kinds of pipes, same kinds of this, same kinds of that. What's the primary difference between now and 1935? How deep could we drill in 1935? It's a bit deeper than that, but good guess. Probably maximum depth in the 30s was 8,000 or 9,000 feet, maybe a little more. And what happened was, this is a government book, and we all know about government books. They should be made out of toilet paper, but this one in particular is USBM, United States Bureau of Mines. And it is monograph 7, 1935, and it is designed as a book for people to evaluate gas well performance. And the purpose of that was to estimate the maximum flow rate. Now, using this equation, we have this constant thingy C, and we have this other constant thingy N, and then we have these variables, which we can see are P bar squared and PWF squared. Now, PWF, unfortunately, is measured down here at the bottom of the well. It's not measured at the surface. We take the surface pressure, wherever you want to measure it, I guess right here. That's called PTF. The T is for tubing, the W is for well, and the F is for flowing. And so somehow we have to come up with a magic algorithm to convert PTF, to PWF. How do we do that? How many of you had Dr. Valco's class successfully? Any repeaters? Yeah? Okay. So somebody tell me, what equation do we use to convert surface pressure to bottom hole pressure? I'm up here without a net, people. Give me a hand. Somebody. Okay. What's the name of the equation? Is it the Berlusconi equation? Did you hear what he said yesterday? He's the Prime Minister of Italy. He said that they needed to use the military to protect Italy's women because they're so beautiful that the cities are turning into, areas where they're not safe and that sort of thing. Nice thing for the Prime Minister to say. No, it's not the Berlusconi equation. Is there another equation like that? What's that? Italian spaghetti, Berticelli? No, that's not it. What's the other one? The Bernoulli. Oh, that guy. Yeah, okay. So it's an energy balance, and it's going to have some terms in it. One will be friction, one will be gravity. There may be some momentum terms as well. But what do we know about the trip from the bottom of the well down here which is PWF, to the top of the well up here, which is PTF. If we think about this in reverse, what happens along the way? What do we see? Do we see little deer? You know, something like that. And do we see a hunter over here? This is Mr. Stone with his bazooka, and he shoots the deer. No, we don't see that. What do we see? What's the temperature profile look like? Is the temperature high down here? Yeah. And so it gets lower as we go up, so temperature versus depth is going to look like that. Is it linear? Probably not, but we can probably say it is and tell ourselves a little lie. What else happens along the way? The pressure changes. So we're probably going to have to segment the wellbore and look at behavior over little segments, right? Remember your finite difference calculus that Dr. Maggard taught you? Some of you more than once, perhaps? No? Okay. So we have to break the wellbore up into discrete segments. We could cheat and do it all in one segment. We talked about that, or maybe you did with Dr. Valco, I don't know. Dilhan, what else goes on between the bottom of the well and the top? Oh, liquid. Yeah, that nasty liquid stuff. Because as you go up, the temperature goes down, and the pressure goes down, and what happens to gases? They like to drop out little particles of liquid. Sometimes it's water, sometimes it's condensate. So we have to factor that into it as well. Interesting. So no matter how sophisticated we become, are we ever going to be able to take this measurement and absolutely 100% correctly convert it to bottom hole pressure? I'm just pointing this out, so if you're ever tempted to use surface pressures for your analysis, and you will be, because you're going to be in seminars with people from the industry who buy you lunch and sell surface data acquisition, that you don't need no stinking bottom hole pressures. We can do it for you, and we can calculate it. Recently, I saw something very unusual, and I'm trying to think of where this was. Off the top of my head, I'm not recalling. Oh, I know where it was. Sorry. It was an oil reservoir, and the surface pressure as a function of time, PTF, versus time, went up. And the bottom hole pressure, because they had a measurement system permanently installed, which way did it go? It went down. Dilhan, have we seen that before in gas wells? No. Usually they track each other, at least directionally. But in this case, it was a volatile oil or a high gassy oil, and they were using electric submersible pumps as well, and the surface pressure actually went up as a function of time, while the bottom hole pressure went down. Kind of weird. Not supposed to do that. But these are measurements, and we assume they're correct, so something strange might happen. So you can't really just throw a dart at it and hope for the best. Now, this equation, where did it come from? What does empirical mean, Z-Dog? Is it empirical if you see me feeding my pigs and assume that they're my pigs? Yeah. Okay, so is it empirical that if we see a plot of what? A plot of delta P squared versus rate on a logarithmic scale, both of these. This is squared, sorry, not Z. What's it going to look like? It's supposed to be a straight line. Interesting. This book that I'm talking about, and it is available as a supplemental text in your in the reference section of Petty 324, is devoted to this equation. The entire book, or at least the first part of it, is devoted to this particular equation. And they look at dozens of cases of what's called 4-point data. Why is it called 4-point data? 1, 2, 3, 4. So they took 4 measurements, and they used those to make this plot. So that was a 4-point method. Can it be derived analytically? 3 options. Okay, what's the right answer? If you assume what? Sorry? Okay, but what else? Sorry? Okay. More importantly, we talked about this in 311. Has to be steady state, non-time dependent, right? Okay, so under those conditions, yes, you can derive it. Now, can we derive this for pseudo-steady state? Not exactly. We can get close, and it's probably right. There are other forms of this, for example, the pseudopressure form that can be derived for steady state exactly, but the pressure squared form is not exactly correct for pseudo-steady state. What about for transient flow? Is this correct for transient flow? Remember what transient flow means? Come here, Dilhan. Let's use you as the example. Of course, you'll know where you are because you can see the light, right? So you have to act like an idiot. Okay, we're putting a blindfold on him. Turn around, turn around, turn around, turn around. Okay, walk until you run into the wall. That's transient flow. Okay? Whenever you're going along and you don't know there's any boundary, then that's transient flow. Is this going to work for transient flow? What was another name for transient flow in the 50s? No. Why don't we go to Marmina? Okay. Pseudo-steady state is like steady state, except that the profile changes in time. Okay. Steady state, the profile doesn't change in time. Now, transient flow has similar characteristics to steady state, but at a snapshot in time, we have to look at it, and its characteristic behavior is identical to steady state, but the position moves. It's propagating out. So as he walks out in the reservoir, he's the pressure distribution propagating out in the reservoir. So that relationship is more or less maintained. Not exactly, but more or less maintained. So they actually called transient flow successive steady states. So while he's walking out there, if he's got a tape measure and he says, I'm 10 feet away from the point, the wealth point, then I know my position and I know the pressure gradient is going to be approximately steady state. And then he takes another step, still approximately, so it's a succession of steady states. That's fine. We don't really use that for anything other than to try to explain conceptually that for radial flow there's a succession of steady states. So this equation, where is time in this equation? Does anybody see time? Okay, so you would say that time is here in P bar? Okay. But how can you then relate rate and time? See, this equation is not Q as a function of T. It's Q as a function of P. And then we need to know P as a function of T in order to estimate Q as a function of T. But that's a whole other story. Okay. So Dilhan, you got any tricks up your sleeve to convert this to a Q as a function of T? Now, we'll have to explain that to him later. What we'll do is we'll take this equation and we'll couple it with a material balance equation, and that will give you P as a function of T, actually P bar as a function of T, and that'll allow you to write an equation. But right now, can you use this equation to predict rate as a function of time? No. What's the only thing that you can use this equation for? Marmina? You're supposed to say maybe. That's your answer today. Okay? So, what happens, Marmina, if this goes to 0? That's the maximum pressure drop squared, right? So that would mean that we would come up here and read off the graph, come down here, and this is the AOF, the maximum flow rate, the absolute open flow. It's a fictitious number, right? The other day, a friend of mine was looking at an old well report, and the highest reported rate for the well was 5 million cubic feet a day. But the reported absolute open flow was 25 million cubic feet a day. Almost a factor of 10, or at least a factor of, 8 or so higher, right? So what happened? I said 8, I meant 5. It's a flu.
Pressure got as big as it's big.
No. There was no 25 million a day. It was this number. Oops. It was the AOF. They were reporting a calculation. When you read the newspaper and you see someone reports an absolute open flow, it never flowed that much. It may have flowed 1/10 that much. It's a fictitious number. So would you estimate reserves based on the ability to flow at one particular time? No, of course not. That'd be very, very dangerous. Sorry?
So what's the point of having it?
Excellent. You get a hug, okay? So why do I want to... You've been away too long, son. Why is that the best question that's been asked in this class so far?
We don't know.
But why do you think people calculate AOF? Let's say you 3 fellas don't like each other, and you each own property. He's got a well, you've got a well, you've got a well, all in the same reservoir. He's got a better part of the reservoir, so he can produce at a higher rate. You've got the worst part of the reservoir, so you have to produce at a lower rate. But if you calculate the AOF, and then you go to the government and say, government, he's going to take all my gas, because he will. He's got the better part of the reservoir, and it's just going to draw from you. The government will look at that, and they'll make a proration factor based on his AOF. So he cannot produce at his maximum allowable because he will drain you two. And you're wondering, what the hell, how did this happen? Because in the early days, there were no laws, and people did whatever they wanted. And so somebody had to come in, and he was a railroad commissioner or maybe the USBM or somebody, and they said, you guys have to practice what's called conservation. And when you look at old books, they'll talk about conservation and proration, and what they really mean is you're stealing his gas. So we're going to stop you from doing that. It's imperfect. It's not a technical solution. It's a legal solution. But it worked. Now, how many places in the world are on proration right now? Not very many. How many places are on proration in Texas? Definitely not very many. Okay? How would you deal with this today? If you owned a field and you did not want to, and you had partners in that field and you didn't want to be prorated, how would you handle that? Sorry? Louder. That actually is a good question. I hadn't thought about that. Let's say that I am the most wealthy of the companies in there. What should I do? What's a simple solution? Make them an offer they can't refuse. And this actually happened a couple of years ago. Encana bought a field in Robertson County. They had partners. And they paid them $2.6 billion to get out of it. And it looked like it was a bad idea at the time, but they found this fantastic reservoir, very high permeability and high porosity out in the middle of nowhere in a very low turbidite environment. And they made a hell of a lot of money out of this. But it was a strategic decision that they decided to buy out their partners. And at the time, nobody really thought it was a good idea, but they did it, and it worked. But, you know, the Canadians are Boy Scouts, no offense if you're Canadian, and they do things like that. Okay, so this is a derivation of this relationship. Dohan, this would be a good quiz question, right? Maybe for Wednesday? Yeah, so they can study that. And this is that concept we talked about a moment ago, this 4-point plot. And I'm just going to make up 4 points here. So there's 4 points, and we're looking at the pressure drop squared and the rate. And then they've drawn a line through this. Mr. Stone, you like this line?
That's pretty good.
Yeah? Now, what would happen, Mr. Stone, if you came in and you had some governmental pointy head that said that that's the line you're going to use from now on? How does that affect you? Because now, when you come over here, your AOF from that thing is much less than your AOF from that thing, right? Now, we knew all along that the straight line wasn't true. How many points does it take to define a straight line? Who wants to take a shot? Somebody new. Thank you. Anybody else? How many points does it take to define a straight line? 2. Except in Texas, where it takes how many? 1. How do you get away with that? Because they take 1 point and then they force a slope on it. Okay? That's legal in Texas. It used to be legal to have an open container in the car. You know, it still is legal to have a gun in an open container, right? But, this is being recorded, please, Ted. Okay, so what about this other thing right here? What does that look like? For an A in this course, somebody tell me. Rain Man, shut up, okay? Sorry? The question was, what does this look like? Oh, it looks like a hockey stick. Looks like a puppet. Looks like the trilogy of the ring, right? Okay. Anybody else? Sorry? Oh, jeez. Okay. I deserve that. Okay. Let's try it another way, girls and boys. Miss Leva, you're sitting close, so you ready? Good, even better, okay? So it's going to look like this. There'll be a straight line portion. That's a unit slope. And then it's going to peel off like this. What does that remind you of? What's on the y-axis? Speak up, honey. You said the friction factor? And what's on the x-axis? That Reynolds number thingy? Okay. And what this is called is what? Laminar flow. And this is what's called non-laminar flow. We don't call it anything else. And this is the same that's true over here. That's the non-laminar flow portion. A lot of people forget that gas wells that produce at high rates have non-laminar flow portions, so this is something to think about. Now, what if your company, Mr. Stone, and I'm using this loosely, decided that you were going to stay within the state-mandated straight line method, and you're going to use a straight line? But Ms. Sleeve over there, she works for Exxon, and she says, I'm always going to do things the right way. Mr. Stone is not a reputable businessman. He's not willing to do things the right way. And so she comes over here and she estimates her open flow and you estimate your open flow. What's going to happen? It's a trick question. She's going to sue you into oblivion because she's got Exxon's army of lawyers who live for little discrepancies like this. Well, what happened when the blue line was proposed to the state of Texas? Anybody? Sorry?
If they regulate the flow, she'd get a
Right, but what happened whenever there was a proposal made to the state of Texas to adopt the more conservative method? What happened? People went nuts. They said, if I do it the right way and he does it the wrong way, he still gets more favorable treatment than me. So why should I do it the right way? Okay, you ready for this? This is a little what we call social engineering experiment. So can someone tell me where you're forced to use the blue line? Anybody? Speak up. Acapulco. What? It's another country? Sort of. Does start with a C and ends with an A. Canada. In fact, it's the province of Alberta. You are required to use the blue line. Interesting. Okay. It's almost time. Remind me when they get 10 minutes for their quiz. Okay. This is a real easy question. This is where things come into the well, and this is where things come out of the well. And then, of course, this is where we sell stuff over here. Well, that's water, so we're not going to sell the water. In fact, we have to pay for it. But what happens on this little trip? Lots of different things. What's our favorite thing that happens along this trip, Dilhan? Leaks. Believe it or not, boys and girls, you will encounter wells in your lifetime, in your very near lifetime, that will leak. Yep. I hate to tell you that, but it's true. Okay. Maybe old perfs, maybe a bridge plug, maybe something slipped, maybe Joe Bob, didn't seat the casing right or something, but you will deal with leaks. You'll also deal with multi-phase flow and other problems like that. We are only interested in what happens at the reservoir. But getting to the reservoir, our good friend, the well completion, is going to make us very unhappy from time to time. So make sure that you have the completion report in your lap. The tubulars, part of that, the surface facilities. I've seen some mighty strange things when it comes to pressure transient testing. I had a friend who performed a surface pressure transient test. The gauge was right here. They were using, there was a tank battery, and in the tank battery they had a valve over here. They shut the valve in, and over here, when the pressure got to 999 psi, let's say, the pressure built up, and then it just flattened out to 999. I'm making this up, of course, but like that. That was the surface pressure. Somebody tell me what happened. Louder. I hadn't thought about that, but no, the gauge went to higher than 999. Thank you. Anyone else want to guess? Where do you find something? The last place you look. Okay, so when do you discover enlightenment? From your last question. So I went through 100 questions with these guys, and it was a couple of, ne'er-do-well classmates of mine from Texas A&M who formed their own company and have made and lost millions of dollars. And this was their very first well test they had run on their own. And the last question I asked, I said, "What kind of valve is this?" And they said, "It's a closed valve. You don't need to know any more than that." And I said, "Well, what kind of valve is it?" And they said, "It's a dump valve. It's set for 1,000 psi. And I said, "You guys didn't realize the well went back on production?" No. "Well, what can you do with this pressure data?" Nothing. Okay. They didn't really care. All right, so let's go down. Let's close this guy. All right, so the thing that I want to leave you with is during pressure transient analysis, and I want you to think about this very carefully, you're going to be using a surgical knife. Sometimes, you can chop a tree down with a surgical knife, but it's not a very good idea. So whenever you're using pressure transient analysis, make sure you know what you're focusing on. You're looking at an event in the life of the well. Now, what's happened in recent years is the dominant vendor has begun to work quite exclusively with numerical modeling. They like this. That just means things are much more complicated. The more complicated you make the model is not necessarily a better answer. Then there's something called deconvolution. Deconvolution is like perpetual motion in petroleum engineering speak. What happens is we always want a constant rate system because that's easy to analyze. So what we've done is we've taken some mathematical relationships and created deconvolution algorithms. Now you may be saying, you seem to know a lot about this. Yes, I do. And 20 years ago, I wrote a dissertation on it, and it sits on a shelf, and nobody uses it, and blah, blah, blah. And then 15 years later, somebody over on that side of the room came up with yet another method of doing deconvolution, and your thesis sits on a shelf, and maybe how many people in the world have read it, and even though it might have been pilfered for a software program or two, nobody else really cares, right? So deconvolution, you got to be careful with that. Just be aware of it. Better data analysis functions, we've been working on this. Maybe we can help you. Now, when you start looking at production analysis, you have to have better measurements of pressure and rate. If you're going to look at pressure and rate measurements as separate entities, you're always going to have a problem. They have to be coupled. You don't have to have a measurement at exactly the same frequency, but it'd be real nice if you did. The pressure conversion problem is driving me nuts. Let's just go on ahead and install something at the bottom of the well. You can do that, by the way. There are systems. Looking at some more solutions for this, it may help us get around some of those nasty reality checks, some of the things we talked about a moment ago. And then looking at diagnostic methods that allow us to see features in production data the same way we do pressure transient. That's one of the things I want you to be aware of as well. Okay. And then these are some of the questions that you may want to consider in pressure transient analysis. And what I want you to think about is, yes, whenever you look at the software, this morning, I had a phone call from another professor in another university, and he was trying to analyze some, what's the right way to put this? I guess without betraying the name of the reservoir, a shale oil reservoir that is very difficult to produce. Somebody had asked him to look at some well tests from it. Well test analysis is not his specialty, so he asked me for some help. What do you think the data look like? Is it good data, bad data, happy or sad data? What do you think? Marmina? They wouldn't have given it to a professor if it was any good. It must be garbage. And it pretty much looks like it is. And what do they want to know? They want to know, can you get reservoir properties out of this? Well, you know, that's why there are consultants in the world, because they can get an answer out of anything. I'm still a little bit concerned every time I look at the data sets. And Dilhan, I'm going to point you out to where they are so you can take a peek too and beat your head against the table. Now, what we can do is we can come up with qualitative analyses, but quantifying reservoir properties is going to take good information. I just want you to remember that. We're going to give you a problem one of these days on estimating average reservoir pressure from either a long pressure buildup or a long pressure fall off, but that's okay. We'll come to that later. What usually goes wrong in pressure transient testing is the setup. Something, you know, you need to model it, make sure that you have all of the things taken into account. This is where you excel. You guys all grew up with computers, so make a simulation grid. It doesn't matter whether it's analytic or numerical, but make a grid of possible values. You know, try a low permeability, try a high permeability, try a low storage, try a high storage case, and see what it looks like. Then preparation of the well for testing. Please don't walk up to the well and turn it on or off. You're going to cause something terrible to happen. You have to include the entire production history. It will corrupt the interpretation if you don't. By the way, this gentleman sent me only the production history he wanted me to see, and I said, where's the rest of it? And then he forwarded that later. How nice of him, huh? The well completion, you keep the records in hand. And then why are you testing this? If you don't know why you're doing something, stop. You know, I can't tell you enough that a bad example or a bad case will kill you ever doing something again. So if you just decide, we're going to do this, something bad could happen. I've seen cross-well tomography surveys. These are near seismic, reservoir seismic or close-in seismic type surveys. I've seen those go completely belly up because somebody didn't do their preliminary work. They didn't think about what their objectives were. It has nothing to do with pressure transient testing. And I've seen another one where management said, you know, we are going to inject CO2 in the ground by the end of the year. We are going to demonstrate this on our worksheets, that we are going to inject CO2 at the end of the year. So sure enough, they injected CO2. And what happened, Marmina? They expected 6 months later to see a response at the well where Mr. Stone is. And what happened? Nope. 3 hours later, the CO2 showed up in a well 4 patterns away at another operator's lease. And they called up screaming bloody murder. What the hell is going on? You know, we've got a gas well on our hands. Logistically, it's supposed to be impossible. But, you know, this reservoir had been hydraulically fractured to smithereens. The CO2 just found a way to get there. And once it decided where it was going to go, can you change its mind? No. So that was a waste of time. You're looking at high resolution, high frequency data. Remember that. And you only get a snapshot of the reservoir. You only get to see a piece of it. Okay. Now, when we start talking about production data analysis, it's low resolution, low frequency, and you're looking at the entire life. So you have to be kind of careful about that as well. Okay, ready to give these out?